In exercise 915, we're looking at oxymercuration-demercuration from the perspective of synthesis, so hopscotching from reactants to products. So we look at our reactant, we see an alkene, a hydrocarbon with a double bond, and instantly the big category that you want to think of is addition, as opposed to substitution or elimination. So we're going to be doing addition. Well, what two things do we add? We look at the recipe, and you'd recognize the recipe for oxymercuration-demercuration. You put mercury on and an oxygen on, that's oxymercuration. You use sodium borohydride to replace the mercury with a hydrogen, so that's demercuration, as we discussed in a video on the concepts behind oxymercuration-demercuration. So this adds an H and an OH, and it adds it in a Markovnikov way. H always goes to the carbon with the carbon bonded to fewer carbons, so the less substituted carbon. Now that is exactly like acid-catalyzed hydration. Acid-catalyzed hydration, you just need water and an acid, so those are both very inexpensive and safe, relatively safe, whereas here you're dealing with this mercury compound and special boron compounds. Those are both expensive and can be kind of dangerous, certainly bad for the environment with mercury. So why would you ever do this? What's the difference? Why wouldn't you just always do acid-catalyzed hydration? And the difference is that you do not get rearrangement with oxymercuration-demercuration. And you'll see that in each of these examples, or at least in these first two examples, you'll see that you don't get rearrangement, whereas you would with acid-catalyzed hydration. So let's first just draw the oxymercuration-demercuration product, and then we'll also draw the acid-catalyzed product to compare. So with oxymercuration-demercuration, you are adding two things onto the molecule, H and OH, and it is going to be Markovnikov. So Markovnikov addition. So that only involves the pi bond. You can redraw the molecule with all the same sigma bonds. Just don't include the pi bond there. Now if you look at the two carbons in the double bond, the one on the right is only bonded to one other carbon, so that is primary, and the one in the middle, that's bonded to two other carbons, so that is secondary. In Markovnikov addition, the hydrogen goes to the less substituted carbon, so that's going to go here. Now with oxymercuration-demercuration, you don't have to worry about carbocation rearrangements. The lone pair on the mercury and the stabilizes the carbocation by forming that mercurinium ion that we saw in the video on the concept behind oxymercuration-demercuration. And so the OH always adds to the other carbon in the double bond, the more substituted one. So that's the product you'd get with oxymercuration-demercuration. But compare that with the product you would get from acid-catalyzed hydration, and that can be written in several ways. It can either be H3O+, or they could give you water and an acid like sulfuric acid, either one. In that case, you still add hydrogen first. Hydrogen goes on to the less substituted carbon. So you draw the same carbon skeleton. The hydrogen, it's Markovnikov addition, so the hydrogen would form here, and you'd have a carbocation on the more substituted carbon. In this case, though, there is no mercurinium ion that can stabilize that. So that carbocation is free to rearrange. Now it's secondary here. To the right, it would be primary. To the left, this carbon is bonded to 1, 2, 3, 4 carbons. Right now, it's quaternary. And if there's a methyl shift, if this CH3 picks up its electrons and moves over, then you would end up with a tertiary carbocation. Oops. So that is a tertiary carbocation. That carbon is bonded to 1, 2, 3 other carbons. It's tertiary, which is more stable than the secondary. So with acid-catalyzed hydration, you get this rearrangement, and the OH ends up attacking, really water, ends up attacking that tertiary carbon, the OH ends up adding here. You can see how different of how different the reactants and the products are here. In the case of oxymercuration-demercuration, you do not get rearrangement. In the case of acid catalyzed hydration, you do get rearrangement. That changes the carbon skeleton, this methyl group moves over, and it changes where the OH attaches. So you could see that small difference, what seems like a small difference of rearrangement, ends up having a big effect on the product that you would predict. So for B, we'd first, if you saw this out of context, you'd see that alkene there, and instantly your mind should go to addition reactions, not substitution or elimination. So we'll do addition. What two things are we adding? You look at the recipe, you would recognize oxymercuration-demercuration. You're adding an oxygen from the water and a mercury from mercuric acetate. So that's oxymercuration, and then you're taking the mercury off with sodium borohydride, replacing the mercury with one of those 4 hydrogens. So oxymercuration-demercuration. And in oxymercuration-demercuration, you add an H and an OH in a Markovnikov way with no rearrangement. So we're going to redraw that molecule. We're going to add H and OH, but it's Markovnikov, so the H has to go on the less substituted carbon. In the double bond, the carbon on the left is only bonded to one other carbon. It is primary. The carbon on the right is bonded to 2 other carbons, so it is secondary. The addition is Markovnikov, and so the hydrogen goes on the more substituted carbon. I'm sorry, the hydrogen goes on the less substituted carbon, here the primary one. And that means that the OH always goes in oxymercuration-demercuration on the other carbon in the double bond, the more substituted one, because there is no carbocation rearrangement that we have to worry about. So just to compare, imagine if you did acid catalyzed hydration with that same molecule. So either H3O plus or water and sulfuric acid, really any strong acid. A strong acid is just going to donate its H pluses to the water and give you H3O plus. Well, if you did that, after the first step, you would get Markovnikov addition of the H, and the other carbon in the double bond would have a carbocation. That would be a secondary carbocation. The carbon next door is bonded to 1, 2, 3, 4 carbons, so that is quaternary. You could have a methyl shift, so one of these CH3s picks up its electrons and moves over to give you a more stable tertiary carbocation. And in the case of acid catalyzed hydration, the water ends up attacking as a nucleophile to the carbocation. And so where you have the carbocation, that's where the OH ends up attaching. So notice how different of products you get when you do oxymercuration-demercuration, which just is Markovnikov addition of H and OH, but without rearrangement, versus acid catalyzed hydration, which is still Markovnikov addition of H and OH, but with rearrangement. Okay, this last one wouldn't have rearrangement, so I'm not going to draw the acid catalyzed product. In this case, you would get the same answer for both of them, and acid catalyzed hydration would really be the more efficient reagent. But if you wanted to draw the product of this, you'd look at your reagent, you'd see, okay, I have a double bond. That means the big category I want to think about is addition, not substitution or elimination. So addition. What am I adding? You look at the recipe, you notice oxymercuration-demercuration. You're going to add mercury and an oxygen from the water. That's oxymercuration. And you're going to replace the mercury with one of the 4 hydrogens in sodium borohydride. So that's the demercuration part. So oxymercuration-demercuration. In that case, you still get the same carbon skeleton, but without the double bond. And then here, it's Markovnikov addition, so the H adds to the less substituted carbon. This carbon here is only bonded to one other carbon, so it's primary, whereas the other carbon is bonded to 1, 2, 3 other carbons. So that's tertiary. Because this is Markovnikov addition, the H goes on the less substituted carbon. That's there. And the OH goes on the more substituted carbon. And you don't have to worry about rearrangement. And so that would be your product for this oxymercuration-demercuration. So oxymercuration-demercuration adds an H and an OH like acid-catalyzed hydration. But the big difference is that you do not get rearrangement with oxymercuration-demercuration. So hopefully that helps you to think a little bit through how to predict the products of these oxymercuration-demercuration reactions.